Video is basically just an explanation about the paper that we have written about computer vision-based deforestation detection for environmental conservation. And the paper is just shown here on the side, and its introduction is a lot about the state of deforestation in Uganda, which is quite relevant, but will not go that much into that here. Firstly, in the paper, it explains this machine learning methodology that we are using. And then on the top here, you can see that the dataset we are using is the Global Forest Change 2000 to 2022 from Hansen et al. And it consists of 6 different layers that we have been using. The first one is a tree cover layer, which has this encoded grid cells for vegetation above 5 meters. And then the second one is this global forest gain layer, where it says it tracks the forest gain from 2000 to 2012, 1 for gain, 0 for no gain. Forest loss layer encoded 0 for no forest loss and 1 to 22 for the year that the forest loss has occurred. Data mask layer for like no data, land and water. This first layer for like year 2000 with cloud-free images, and the last layer for the same with 2022. And these layers, we split them into grid cells in QGIS. And then we got these tiled images of 100 times 100 pixels, because that's sort of equal to 3 times 3 kilometers, which is what they've used in these other papers that we have been looking at. And then we have been training these different models on this. And then on the right side here, this is an illustration of the whole layer that we downloaded from this dataset. It's 10 times 10 degrees. And then you can see the country borders here in blue. So it's parts of Uganda, South Sudan, Kenya, and Ethiopia. And then this gray square in the bottom corner is the image that we cut out of this raster layer, because we got all of this notification that we had too many pixels. Yes. And then this is an illustration of the different 6 layers. The first one is the forest cover layer, then the first layer, forest loss layer, data mask layer, last layer, and then forest gain layer. And then this is from the tree cover layer, just 9 randomly displayed tiles. These are then approximately 3 times 3 kilometers. And then this one is also just with colored, because we tried coloring the tiles for some of the models that we were running. And then this is more of the EDA, because for example, for percentage of forest cover for each of the tiles, we're graphing this, and then you can see that like there's around 1,000 tiles from 0 to 10 for percent forest cover, and then there are quite a lot, around like 20, 30. And what is important here is that some consider 30% forest cover as forest, some do not. If we consider 30% as forest cover, then 50% of our tiles are forested, but that's not really how they calculate the percentage. In Uganda, there's like 9% forest cover, so they calculate it a bit differently. And then for forest loss, then this first one is a map like highlighting the tiles where there is more than 10% forest loss. And then the second one here, we try to display, because this is encoded for the years that deforestation happened, but this was very unclear and might have been easier, like if you could print it out, very, very huge. And the frequency of deforestation, as I said, this is encoded for years. So here you can see that the deforestation has increased and increased. It decreased a bit since like 2019. I don't know if COVID has something to do with that, but the deforestation has been very, very high since like 1990 to 2005, and in the years after as well, it's been very, very high. And then for computational problems, in this paper we are discussing the black box problem, because we are using deep learning, and then it's difficult to know what is it really using of information, how can it predict these different things. And one solution can be to use simple models as, for example, decision tree, but it will not be able to do the same complex decisions, or integrate it with physical models, but that's not really what we're doing. And then real-time processing of data is challenging because of computational and data storage requirements. And it's also something that we are not really doing because our data set is not updating. And then this last one is inconsistency of data, because this is data from 20 years of time span. And this is also something they mention when we downloaded the data set, that they are using multi-sensor data and there might be these inaccuracies because of that. And also we are looking at forest and not, for example, wetland, which could also be interesting.
Good evening, everybody. This is Hani Abdurrahman from Group 12D. My colleague Suniva has taken you through the first part, and so this is the follow-up to that one. Firstly, I'm going to talk about the dataset that you have used. She has already taken you through how we have broken down our dataset from the Hansen forest change into 6 different layers. And so these layers will cover different aspects in that case. And so for our case, we found it actually relevant only work with at least two. One is the loss year grid, and the other is the tree cover grid. So the tree cover grid shows you the forest cover. It's the layer of the satellite image that's showing the forest cover, the forest abundance, the probabilities of forest that are there. And then the tree cover grid, loss year grid shows you the areas which have lost like the trees. And so comparing these two can enable us to determine some of the features that when you look into will let us know if there's deforestation going on. Moving on to the next slide. Firstly, our dataset is located within our Google Drive. We created an account for our Google Drive, and so I'll share the link to this dataset. As you can see, we have folders that are responsible for holding, for example, our notebooks, and then for holding the tiles of the images as well as the images themselves. Firstly and foremost, what I'm going to take you through now are the models that we have come up with. We decided to come up with 4 models, and of course, one is split into two: the ResNet 15, ResNet 18. So those are 5 models. And in this case, we have used the Siamese neural network, which is used for image comparisons. And then there's the ResNet 8, 15, 18. The difference between the two is that 50 has 50 layers, 18 has 18 layers. And in full, it's called residual network. Then the convolution neural network and the decision tree. So first of all, how are we going to work with the dataset that we have? I've clearly stated that we are using what is called two images, the loss year grid and the tree cover grid. First and foremost, we had to break these down into tiles so that we can work on each tile at the moment. So what we did is we divided the images into a tile of 100 by 100 using our tools that we have for GIS. In this case, we used QGIS in order to split these images. We split images, for example. Now, in this case, the tiles that you're seeing here are the tiles of the tree cover grid. We broke it down into 100 by 100 pixels, and it gave us about 17,900 images, which are tiles. And so we are going to work with each of these tiles one by one. And we also broke down the image of the loss year grid into 17,900 tiles as well. And so we shall pick, like, for example, tile 1 of the tree cover grid, and then tile 1 of the loss year grid, and then you compare the two. By comparing the two images, we shall be able to train our models in order to detect the features that show deforestation. So now we imagine that we have done the grading of the raster layers in QGIS. We now have to determine if this has worked. So this is how we check if our raster layers are there. And then and look here, for example, here it's a scenario of tile 1 from the cover grid, and this is tile 1 from the loss layer grid. If you look at the two and you compare, you can see that for the tree cover grid, we ensure that the red, green, blue light colors are actually popping out. Then for the loss layer grid, you just see and darkness, black areas of black, as well as some light areas and kind of grayish areas, which actually annotate that there's deforestation taking place there. So the comparison of these two images is now where our model comes in. First and foremost, we are using the convolution neural network. The convolution neural network is used for image processing, and in this case, we are trying to what is it called? We're trying to build this convolution neural network in order to compare features of the images and trying to extract those features and view those features in order to determine what we're looking for, using the relevant features in order to do image classification, because now that's where composition neural network is actually very important. As you can see from the table of contents, we had a very organized order of how we're doing it. Then secondly is then Siamese neural network. For the Siamese neural network, it involves comparing two images and trying to determine the likeness between the images. So it is very important, for example, in face recognition, detection, and all that. So in this aspect, you applied it for this case, trying to compare the image from the tree cover, the tiles from the tree cover grid, and the tiles from the loss layer grid. Then decision tree, this one applies the regression, and you're also trying to do classification based on the features that are there. This is also another model. And then the resonate 50. So in this case, this resonate 50, there's resonate 50 and there's resonate 18. And so these ones, they're also called residual network layers. Resonate 50 in this case has 50 layers in comparison to resonate 18, which has 18 layers. And because of that, it is a lot more complex and a lot more efficient, producing more better results, though it requires more computational resources than resonate 18. And then we, unfortunately, in this case, used a dataset from Kaggle. And so we have we pre we here I'm showing you how we worked with the tiles that we have. We imported we first had to mount our drive into our collab. Then afterwards we pre-processed the tiles that we got into red, green, blue, and then we had to resize them to like pixels of 224 to 124 in order, for example, to use it. For the ResNet 50 model, it takes an input of 224 pixels, which is actually important. So the evaluation metrics that we have here, we're trying to look for accuracy, we call F1 score throughout all our models. In our case, we really found it called the convolution neural network to be very important, since it allows you to do classification as well as the extraction of features. Thank you so much.